Welcome back to Physics 142 online. Thus far, we've been talking about how two waves that travel through the same medium at the same time add up to produce interesting kinds of phenomena. We've been talking about standing waves, both for waves on a string and then for sound waves traveling through a pipe. But there's also kinds of phenomena that can occur when we have two wave sources that may start off at different locations but then reach a common point in space. And so we'll indicate this on the sketch using S1 and S2 to represent the two sources of waves, and point P being the location of a listener or a detector who we're going to try to calculate what that person observes or what that instrument observes. And the first kind of interference is due to the difference in path that the waves have to travel to get from the two sources to point P. And you can see in my sketch x2 is a little bit greater than x1 because of the location of point P. So in order to do this mathematically, we're going to make a few assumptions. We're going to say that the two wave sources start off in phase. In other words, if the wave from source 1 starts off as a sine wave, then the wave from source 2 starts off as a sine wave at the same point. They both are in the same phase when they start. And then another word that describes these two sources is that they're coherent. And so if they start off in phase, there's nothing that disturbs their phase relationship while they're traveling. Okay, so in addition to being in phase and coherent, these waves have the same amplitude, the same frequency, and the same wavelength. The major difference here is that they just travel different distances to get to the detector. So we can add the two waves up and see what we get. The standard waveform, even though these generally are going to be the sources of sound waves, and sound waves travel outward in all directions, we're just going to consider the propagation along a particular direction that gets to point P. And so we will approximate these sound waves using the standard form for a wave traveling in a single direction. So if they have the same amplitude, we factor out the amplitude, and we get cosine of kx1 minus omega t plus cosine kx2 minus omega t, where x2 and x1 are the distances shown here in the sketch. So we now can use the identity that we've used several times for adding together two cosine functions, and we end up with the product of two cosine functions as the result. Now, let's look at this result carefully. You'll notice that the second term on the right-hand side looks a lot like the individual waves, because it's k times some kind of a distance, and in this case the distance is the average of the two distances, minus omega t. So this term at the end has the same mathematical form as a traveling wave. So the sum of the two waves produces a net traveling wave that gets to point P. But look what's out in front of that traveling wave. Not only do we have 2a, but we've got a cosine term that doesn't depend on time, but does depend on the difference of those two distances, x1 and x2. And so we can think of this entire term out in front of the traveling wave as an amplitude that depends on position. Because if point P is in a location where x2 and x1 are different, then depending on how different they are, that will determine the amplitude. And we have some very cool things that can happen when x2 and x1 differ by just very certain amounts. So let's consider the phase difference, and we'll use delta to indicate this, between the two waves. Now what do I mean by phase difference? The term in brackets after the cosine function for each of the waves, those are called the phases of the waves. And so what you notice is that if you subtract those two, what you get is k times x1 minus x2, and the omega t terms drop out. Alright, so the phase difference between those two waves is what we're going to indicate by delta. And like I said, delta is just k times x2 minus x1, or x1 minus x2. It really doesn't matter. Generally, we'll write it in such a way that the larger one comes first. So we will call that difference in path delta x. It's the extra distance the wave has to travel to get from S2 to point P compared to S1 to point P. Using the definition of k as 2 pi over the wavelength, then this phase difference is just 2 pi delta x over lambda. Now we're defining this so that we can simplify the expression for the sum of the two waves from the previous slide. So what that means, if you go back and look at that expression, if I substitute for k times x2 minus x1, that's delta, and there was a factor of 2 in the denominator. So all this does is rewrite that sum of the two waves in a slightly more compact form. And it helps us understand what values of delta will produce special kinds of effects, because this cosine term out in front can vary all the way from 1 or negative 1 to 0. So let's consider those two possibilities. If this cosine term is 0, then the net wave will be 0, and the two waves will interfere completely destructively. So in other words, at special points P, even though you're getting waves from both sources, you would end up with a net wave of 0. And that would be a location in space where the sound is just, there isn't any sound. The amplitude is equal to 0. So mathematically, how does that work? Well, the cosine term has to be 0, and we know that cosine is 0 when the argument is pi over 2. And then again, 3 pi over 2, 5 pi over 2. So multiples of pi over 2, where delta then would be pi, right? That would work. And then 3 pi, and then 5 pi. Those will give us the odd integer multiples of pi. And that will produce the condition for completely destructive interference. Now let's express this going back to the definition of delta up here. If delta is 2 pi delta x over lambda, for each of these values of delta, I can solve for the path difference, delta x. So for example, if delta is equal to pi, right, then delta x will be equal to lambda over 2, just solving that equation for delta x. If delta is 3 pi, then delta x is 3 lambda over 2, and so on. Now what does that mean? That means that the extra distance the wave has to travel to get from S2 compared to S1 is a half integer multiple of a wavelength. So 1/2, 3/2, 5/2, and so on. If that path difference is equal to any of those values, then at the location P, you won't hear any sound at all. And that's destructive interference. Now the other extreme would be constructive interference, right? That would be where the cosine of this argument delta over 2 is equal to 1. And so that happens where delta is, or negative 1, 1 or negative 1, doesn't really matter. So that would happen where delta is equal to 2 pi, right? Because then that would be cosine of pi. It'll happen again where delta is equal to 4 pi, because that would be cosine of 2 pi, and so on. So the difference here is when delta is an even multiple of pi, then we get an amplitude that has its maximum value, either 1 or negative 1. And if I do the same thing with the top equation, take that top equation now and solve for delta x, for each of these values of delta, we get the integer multiples of lambda. So these are just two special cases, and that means that there are points in space where you'll hear a very, very loud sound if you've got completely constructive interference, and then there are other places where you'll hear a very soft sound and ideally no sound at all. And that's where the path difference is a half integer multiple of the wavelength. Now this may be a little bit confusing. Let's think graphically. Let's draw a picture to try to illustrate these two different cases. So here is my attempt to illustrate this with sine waves traveling from S1 to point P and S2 to point P. So they start off together. So in other words, when they leave S1 and they leave S2, the sine waves are in phase with one another. But because there's an extra distance that has to be traveled from S2 to point P, then when they add up together at point P, we have to look to see whether their peaks are lined up or whether they might have a peak lined up with a trough. So the sketch on the left shows completely constructive interference, which means that the peaks, when they get to point P, the peaks for each of those traveling waves are together. And that means that the sum of the two waves will be an identical wave with twice the amplitude. And what happened here was the extra distance that had to be traveled, which was S2P minus S1P, was equal to an integer multiple of a wavelength. Right? And so if I count wavelengths here from S1 to P, there's 1, 2, 3, and a little bit more, right? And then from S2 to point P, there's 1, 2, 3, 4, and a little bit more. And so the difference in path here was just a wavelength. Now the case where you have destructive interference, that's where, although the waves again start off in phase when they leave S1 and S2, by the time they get to point P, from S1 the wave has its peak, but from S2 the wave has its trough. And so the positive and the negative amplitudes added together produce 0. So this would show completely destructive interference, and if you count the wavelengths again, you'll see that the path difference in this picture is 1/2 the wavelength rather than the wavelength. So hopefully these two pictures show you what's going on when we have this spatial kind of interference. And I call this interference in space because depending on where you are in space, you might hear constructive interference, which would produce a loud sound, or destructive interference, where you wouldn't hear anything at all. So that's interference in space, and it happens because of the path difference between the two waves. And there's some really cool problems that we can do to apply these equations. The second type of interference I call interference in time. And the difference here is, once again, you've got two sources, S1 and S2, and the waves are going to travel, to keep things simple, let's just assume the waves travel the same distance to get to point P. So point P is equidistant from the two sources. The only difference with the two waves now is they have slightly different frequencies. Same amplitude, same wavelength, but slightly different frequencies. So we want to know what happens to the net wave at point P at all times. So once again, we add the two waves together. Only now, since these two waves have slightly different frequencies, we've got an omega 1 for the first wave and an omega 2 for the second wave. All right? So the total wave is the sum of those two. Once again, we can use the same identity, and what we see is, again, the second term looks very much like that of a traveling wave with a frequency that's equal to the average frequency of the two waves, omega 2 plus omega 1 over 2. But it still has the form of a traveling wave. But notice that the term out in front is now an amplitude, but it depends on time. It's a time-dependent amplitude. And this is why I call this phenomenon interference in time, because this term will vary in time with a frequency equal to half the difference of the frequencies between the two sources. And so that means if I'm at point P listening to this happen, there will be some times where I will hear a very, very loud tone, and that will be where the cosine function, where the cosine function is equal to 1 or negative 1. Then there will be other times where the cosine function goes to 0 and I won't hear anything at all. And so the result of these two waves being traveling together through the same medium and reaching the same point is there will be alternating loud and soft tones, even though the person who's listening will be standing at the same point and will not be moving. So let's just summarize this. The net wave is a traveling wave whose amplitude rises and falls in time, and we call this phenomenon beats or beating. The beat frequency is given by simply the absolute value of the difference in the two frequencies, because it doesn't really matter which one's higher and which one's lower. It's the difference that counts. Now, if you look at the previous slide, you'll see that I said this amplitude has a frequency of half the difference in the two frequencies. So then why does the beat frequency not involve that factor of 1/2? And here's, if you look at this sketch, here's the reason. This shows three waveforms. The red and the blue are the two waves being added together. And you can see they have the same amplitude, but just slightly shifted frequencies. So I made a plot here using frequencies of 20 Hertz and 23 Hertz for the blue and the red. When you add them together, you get this interesting pattern, which is shown in the yellow, where you can see the amplitude reaches a maximum and then goes down to 0, and then reaches a minimum and then goes back to 0 and repeats itself. And so the overall effect has one period that goes from a node to a second node and then to a third node, and that's one period. But we can see in the time it takes for it to go through one period of motion, it goes through 2 cycles of loud, soft, loud, soft. And as a result of that, even though the overall frequency of that wave is half omega-2 minus omega-1, what we interpret as the beat frequency, which is going to be the rate at which the loud and the soft tones occur, will be twice the frequency of the net wave. And so usually though, when we deal with beat frequencies, we're thinking of standard frequencies, F. So the beat frequency F is F2 minus F1. And I'm going to show you a video in just a second that gives a very simple illustration of this, but I'll just say that, you know, this phenomenon of beats is the basis for measuring frequencies using a standard frequency source. Because if you have a standard source and you know its frequency, and then there's an instrument or some other source of sound whose frequency you want to measure, you can measure the beat frequency, and that will give you then the difference in those two frequencies, and that will allow you to measure the frequency of an unknown source. And musical instruments get tuned in this way. If you have a standard sound and you're trying to tune your musical instrument so it matches that, you just adjust it. For example, with a guitar, you can adjust the tension in the string so that the beat pattern goes away. If the beat frequency disappears, so you can't hear any beats, that means that the two sources have identical frequencies. Alright, so let me just close then by showing you this very short video clip on YouTube that illustrates two tuning forks being played together with the same at the same time, but with slightly different frequencies. .250 Hertz compared to 238 Hertz. You can't really tell much of a difference unless you play them at the same time. Notice there's that warbling sound, that alternating loud and soft tones that we can hear. So we'll try to give another illustration of this in class, but I hope this has been a helpful introduction to these two different kinds of interference in space and then interference in time. And I'll see you in class.